Welcome to Corpstruction, a show about the missions, activities, and employees of the Tulsa District U.S. Army Corps of Engineers. I'm your host, Brandon Parrish. Today, I'm at the Burt Cooper Laboratory at Oklahoma State University in Stillwater, Oklahoma. I'm joined by Dr. Paul J. Tikalsky, the Dean of the College of Engineering, Architecture, and Technology at OSU. Dr. Tikalsky, welcome to the show.
Well, thank you very much for inviting me. I'm happy to be here today.
Well, I want to say I really appreciate you taking the time to sit down, and I know you're a busy person, so we'll try to get back right into it. You do have a beautiful laboratory here, and as I understand it, you were one of the driving forces behind actually making this a reality. Isn't that correct?
Yeah, it was. It was on the books for many years. It just never got built. We had a different laboratory, which was much smaller, but some of the faculty here trained in the same laboratory that I did in Texas, and we knew what kind of great laboratory would build great research. So shortly after I came here in 2012 and 13, we started building the Burt Cooper Laboratory with the help of a lot of industry help and folks, and now it's really a world-class structures and materials laboratory, and we train all of the ODOT technicians for materials testing. We do everything here from microscopy to testing 135-foot long full-scale bridges.
And you were actually a USACE fellow.
I was.
And how does someone get into that?
Well, I back in the early 90s, so I date myself, but back in the early 90s, there was a program in the Army Corps of Engineers that was called CPAR. And this was to attack really big problems and to take expertise from around the country, bring it to the Army Corps' giant laboratories in Vicksburg, and help them address kind of giant-sized construction issues. And so one of the issues they were dealing with at the time was the predictability of masonry walls. So it was complicated mathematics, and so my background was both in structures and materials. But at that time, I was also doing a certain amount of mathematics as well. So I joined the CPAR project, and we did for 2 or 3 summers. I would spend 3 months of my year living in Clinton, Mississippi, and driving over to Vicksburg to do research every single day with the great people at the U.S. Army Corps of Engineers Waterways Experimental Station.
And one of the people you worked with was the quote-unquote father of concrete, Bryant Mather?
Mather, yeah.
Mather, I'm sorry, Bryant Mather. I read an obituary that someone had sort of written about him, and they said that he would go to these conferences, and these engineering conferences, and he'd say, Mather, USACE, or Mather, Corps of Engineers, and the guy who wrote the article said that was one of the most fearsome things that you would hear. What do you remember about him?
Absolutely. I got to know Brian and Catherine Mather, too. His wife were also very prominent people in the science of concrete and cement. And they, from the 1950s on, they developed extraordinary expertise at the Waterways Experimental Station in these areas and did all kinds of work. They were familiar. They were really building off of a lot of the work that the Bureau of Reclamation had done in the 30s and 40s. But the Bureau of Reclamation's lab were winding down, and West just picked it up on a giant scale. And Bryant and Catherine were extraordinary people. They both had a geology and physical chemistry background. And so they took on for their careers learning about this. And I knew about Bryant when I was in grad school and had the opportunity to meet him when I was in grad school, never thinking that I'd ever work with him. But yeah, when he introduced himself at a meeting, I served on several committees with him. Oftentimes in the latter years of his career, I'd be the guy assigned to sit next to him and get him to calm down once in a while when he got excited. But he was a very excitable guy, very precision driven, was very familiar with almost all of the kind of technical things that go on in concrete. He had read every paper you could imagine. If you've written a paper, he knew about it. And even to his last days, he would read and edit stuff. He would send you papers edited that you wrote that you didn't even ask him to edit, and no one asked him to edit, but he would say, you need to add this thing in there and to make this better. And it was always better. It always made it better. So in the 90s, when I got to go to spend time at the Waterways Experimental Station, I had already published a couple of papers with Bryant because early in my career, one of my jobs in the American Concrete Institute was kind of to pull all these old people who had worked with the Bureau of Reclamation and Army Corps together and to capture all of the natural puzzlins that were known in the United States but were no longer used. Now we go into the 21st century today, all of those things are coming back in a huge scale, and if it weren't for those guys leaving a legacy, no one would know where to find them because they're just naturally formed somewhere, and only a geologist kind of person like that would know it. So Brian and I, we got to know each other very well. Catherine passed away, and that left Brian at the lab every day coming in. He had an assistant, and he was hard-working every day right to the day he didn't make it anymore.
Yeah, I recall in the article I read about him, the engineer who wrote it said, like, one thing I learned was you better put a hyphen between words and like adverbs or whatever.
Well, I think one thing he pounded into me is in the word Portland cement. Your spell checker, well, back then even the spell checkers came on, and it always capitalized Portland, but it's not a city, it's not a place, it's an adjective, and so he says, you know, it should never be capitalized unless it's the start of a sentence.
Is it a copyrighted term? I mean, a trademarked term?
No, it isn't. And so Portland just describes the type of cement. There are aluminate cements, there are Portland cements, there are all kinds of cements, and it's just the predecessor word for it that reminded people of the island of Portland in England, where the color stone looks like that. So that's how it got its name back in the 1700s.
Well, I will remember that now whenever I use Portland cement in a sentence.
Don't capitalize
I will
it, right?
not. I will no longer assume that that's a city in Maine or Oregon or somewhere else. So, for those of us who are listening, or for those who are listening who don't know what pozzolans are, can you give us a brief explanation of that?
Yeah. So there's a whole classification of materials in the world that have been known since the ancient times. The Romans used them. They didn't have these kind of manufactured cements, but they knew that volcanic ash from Vesuvius and certain kinds of soils, okay, even bentonites and some of these other kinds of soils, clays, sintered clays and so forth, they, when you mix them with water and any form of calcium, lime or anything, they form glue, exactly the same as concrete today. The glue that holds concrete together is a calcium silicate hydrate with water. And so these pozzolans, which exist all throughout the United States and around the world, are mined, and they were used as additives for a variety of reasons. When we started using a lot of coal, the coal ash,
Fly ash,
right. So fly ash, certain amounts of fly ash were great pozzolanic sources, were great puzzlins. When you just added water and lime to them, they would harden up and make great concrete. When you, eventually we figured out that there was a certain blending of Portland cement and puzzlins, and that would create incredible durability for concrete. So in the 80s, the Resource Recovery Act was finally its provisions came into play in the mid 1980s, which required everybody to use pozzolans in their concrete in order to get rid of all this ash, 25 million tons a year, and a lot of states didn't want to do it, so they withheld their transportation dollars until they complied. But there were certain universities, like the one I was working at, Bryant Mather, the Army Corps of Engineers, the Bureau of Reclamation, Purdue University, these places had done their homework ahead of time, and they created forward-looking guidelines for everybody. And this created, I would say, between those probably 4 or 5 organizations, created a huge change, which now you look back on it, those specifications have saved billions of tons of CO2 into the atmosphere. It's quite amazing.
And where I come from, my part of the country, flash, as they call it, flash, in the Southeast. But that's becoming a little bit harder to get now because of the change from coal-powered plants. So there is sort of a second and third order effect on that you have. And so what do you think is the next great replacement for that?
Well, the supplies of fly ash, yes, used to be abundant, and they used to pay to get rid of it. And then they started in the 80s and 90s, you used to have to pay to take it. You had to buy it. And then by the time from 2000 to maybe 2015, it cost more than Portland cement. And now it's hard to find, and it's a rarity. It's written into specifications, so you must have it. If you're in California or a place like this, it's required, and it's simply not on the marketplace. And so what do you do when you have to fight the regulators on whether you're requiring me to use something that's not available on the market? So of course, we pivoted to blast furnace slags, which the Army Corps had done quite a bit of work with as well. Small amounts of silica fume. These are all different kinds of puzzlins that were industrial puzzlins. And now they're starting to mine out west. You're going back and mining the old sources for the Bureau of Reclamation, which are very large deposits of volcanic ashes that nobody cared about before because it cost more to mine them than it was worth. But now, because of the rarity of it, we're remining these things again.
So here at the Cooper Laboratory here, what would you say is the most unique or surprising result of your research on concrete and pozzolans?
Well, one of the things that's going on here is exactly this idea of, the United States would make about 125 million tons of fly ash a year, but only about 25 million tons were used by the concrete industry because other parts had too much carbon in it, it had something else in it. It was used as scrubber sludge or something like that to take out air pollutants or something. People are going back and remining where they buried this stuff to get the puzzlins back out. So we're now doing a lot of research that looks at how do we reuse this stuff which was discarded and buried in a perfectly good clay-lined landfills, taking up, massive amounts of space, and now opening up those spaces and taking the ash out, improving it, basically removing its carbon, removing some of the other components to it, and putting it back out in the market. So that kind of research is now driving a lot of the work we're doing here and other people around the country, and I'm sure the Army Corps is looking at those same kinds of things. Is that, because it isn't about disposal. It turned out that fly ash really made things last a lot longer. If you used it right and you made concrete well, it would last 100 years, which was always the goal.
And it reduced the cost.
For a long time, it reduced the cost. Now, it's the same cost now, but it reduces the environmental impact.
Really?
Because Portland cement, for about every pound of Portland cement you use, you basically create about 1 to maybe 0.9 pounds of CO2. So fly ash has 0 CO2 associated with it. So if you take out 25 pounds for every 100 pounds of cement, you use 25 pounds of fly ash, you just reduced the CO2 impact of concrete construction by 25%.
Oh, wow.
And so over all those years, it's made a huge difference, yeah.
As the dean, so you were instrumental in getting the lab here up and I guess constructed completely.
Yes.
There's sort of in popular culture, the sort of the trope about the college dean, and they kind of made him out to be maybe this highbrow, somebody who talks like this. But What is the reality for a college dean, especially in an engineering world?
Well, I spent the first, 20 years of my career just research, graduate students, undergraduate students every day. And that's the best job in the world, is get to be a full professor and just work with students every single day. That is absolutely the most fantastic job in the world. Somewhere along the line, I was thrown into the administrator chair because nobody else wanted to sit in it, and that everyone was complaining about something. And we were able to turn it around in the first year or so, and now people had better equipment, they had better opportunities, these kinds of things, and so we started to create success across, not just in my research group, but across multiple research groups. Some of them had nothing to do with what I was doing, but I could understand what they did and could help them facilitate improved facilities, more grant opportunities in recruiting better students and so forth. And so as my career had moved from there to a department head of civil, environmental, and nuclear engineering, and then on to here being the dean of engineering, it becomes just a broader scope. And so somewhere along the way in my career, I just found that my impact, while I was recognized as a fantastic teacher and I did a ton of research and had lots of graduate students and enjoyed all of that, that I could have a bigger impact by facilitating the success of others. And so I started spending my time trying to make others successful and stop worrying about what I was doing. There were other people. When I came to Oklahoma State here, we had Dr. Tyler Lay here. He has very similar background training to me. They didn't need me to be the next face of concrete in the world. They needed Tyler Lay to do that. And what I could do is help other faculty kind of create a synergistic look at all the interdisciplinary problems. I'm sure in the Army Corps you see nothing is one discipline. There's construction, there's electrical, there's sensors, there's concrete, asphalt, steel, there's everything. And all of the people have to contribute to solving the problems. And so that's where my job as a dean really is. Just you're sitting in the background finding out how can I facilitate success for faculty and for students. What do the students need to get to know more about and to get the help they need to succeed in the classroom? Everyone will struggle at something because you're taking, you're a structural engineer, but they're making you take thermodynamics. Well, you need to go find somebody who can help you in thermodynamics. And somebody who's studying thermal will need help in the structural class. So as we look at that kind of thing, what kind of resources? So the dean, honestly, my job is to facilitate the success of others every day. That's all I do. You take care of all the legal, the payroll, all this other stuff, all sits under you too. But we have good people who work on a team, and you create a team that does great work. My research today, my biggest grant right now is a multi-million-dollar grant to help K through 12 STEM, to get more kids to understand that engineering is everywhere. And so we're going to be working on 2,000 kids going to week-long summer camps to learn STEM every year. We're looking at, most of these are diverse kids or people from economically disadvantaged backgrounds. We need to create more engineers, and that's a key item. And helping teachers, not just science and math teachers, but English teachers, music teachers, all the teachers to learn a little bit more about STEM so that when they're talking to kids, they can connect that to the world.
And that actually leads to a question you sort of answered that I had on here. Is there a true engineer shortage, at least in the United States, and how do we address that?
Yeah, absolutely, especially in the South. Where we look, in Oklahoma, we have roughly, we're graduating roughly one engineer for every 2,500 people in the state. So you have 4 million people live in the state. And on average, the United States is about 1 out of 1,300. So currently, there are more than 3,000 open engineering jobs in Oklahoma. And all the universities together in Oklahoma only create 1,550 engineers a year. And some will work in Texas, some will work for the Army or the Navy, I suppose, maybe. But they're going to go someplace, they're going to go where there's a fantastic opportunity for them. So if we look at the armed forces, Tinker Air Force Base and all of their facilities, all of these things take people, and they take technical people. It's no longer about, I grew up in a town where farming, when I graduated from high school, farming or, assembling an engine could be, was thought to be the job you would have for the rest of your life. But the fact is, a farm now isn't a family farm. It's 5,000 or 7,000 head of cattle with 8 people working on it. And that engine is not even built there anymore. It's built by robotics in another state, and the job is making the robots. The job is really creating the automation that's necessary for America to be competitive in manufacturing around the world. And that requires, an engineering degree.
And so, you're not seeing the technology necessarily replace. It actually creates additional jobs, especially in engineering.
Yeah, absolutely. I think we are, the U.S. is in a labor shortage because we have to do stuff smarter, and we don't have enough people who can meet that goal yet. So we need to get more kids to think seriously about math and science when they're going to high school, and then to go on to college in engineering technology, in engineering itself, in any of these other fields that will, in information sciences, all these kinds of things help us, will move forward as a country. And quite honestly, it's the number one thing the DoD, who's funding this big jump in STEM education, they're looking for lots of smart kids and trying to mine them from wherever they might come from. And that may be, I like to use the example of Ratatouille. You never know where you're going to find talent, but if you're not looking, you won't find it.
What advice do you have for students and young people who are considering particularly engineering?
I think, the things we start to look at 6th, 7th, and 8th graders, the middle school is really the key. Kids have to learn to read first. So 4th grade reading skills are really important to become an engineer. If you can't do that, you have a hard time learning anything after that. In the middle school, you start getting exposed to arithmetic and algebra and a little bit of geometry. You get to know biological sciences and so forth. And for those kids, getting them to have that exciting experience in these areas and start asking why. Every time I talk to a young person who's asking the questions of why something works, or when they ask their parents too many questions, I tell the parents, that's the engineer, the person who wants to know why it works, because they're also going to be the person who thinks, how can I change it so it does what I need it to do? And I think that's kind of the seeds to it. In high school, those kids just take the STEM courses, take 4 years of math, take 4 years of science, take 4 years of English. That's really important, in 4 years of the humanities. And that's very important in becoming an engineer, is to get that full education in high school, do well. There are scholarships at Oklahoma State and many other institutions to help you get through engineering school. And when you graduate, you're going to be earning, $60,000 to $90,000 a year. If you took out $25,000 in loans, you're going to pay it all in 3 years, 2 to 3 years anyway. And this is not your biggest problem. Your biggest problem really is going to be the work you have to do in college to get through engineering school.
And that's another I think important issue. Why do you think so many kids are afraid or turned off? And I know the math is a large portion of that, but do we need to improve the way we teach math? Is it that, because you do see in some other countries, they don't seem to have the math issues that we seem to have here in the United States. And maybe I'm wrong.
Well,
there,
if you look at the large countries like India and China, college means going to school for engineering or math. That's the pathway. The humanities aren't at the universities, and so that isn't really the option. You go to the university to study math, science, and engineering. I think that's also, you see a huge part of that in the German system as well, too, where they kind of separate out early people who are going to be technicians and tradesmen and so forth, and then those who will become engineers and scientists. They start diverting their path at age 14, 15, and 16. So in the U.S., I think people people fear the term, calculus, or they fear the term physics. And I think I try to tell kids, when you went from understanding arithmetic, which is, multiplying and dividing things, and they now put it in a word problem. So now they call it algebra. Okay? They use too many X's and Y's and A's and B's to confuse you, but if you just substitute in there the speed of this thing goes this fast, it's the same problem. So it's just different math. When you learn trigonometry, it's nothing to do with algebra and arithmetic. When you learn statistics, it has nothing to do with algebra or arithmetic or geometry or trigonometry. It's just different math. And I think that's the thing you see about calculus. You have to just stop looking at it as it's hard. It's just different. And when you start to think about, I think the thing that calculus doesn't, most engineers, aren't, deriving equations every day for a living. What they're using it for is to think in a way that most people don't think. You've now been trained to think that everything isn't linear. That a pandemic can go exponentially crazy. Instead of saying, well, if there were 40 cases this week and there were 80 cases next week, there will be 120 cases the week after that. Well, that isn't what the actual curve looks like, and I think calculus gets you to kind of understand that, and that can turn around just as fast. So I think in behavior of the world, the natural world actually follows those principles. And that's why it's big in engineering, is because water and heat and biological systems all follow these patterns, not linear patterns.
You worked on a paper with Bryant Mather and it's Jan Olek, and it's about concrete durability. And I'm not sure what year that was from, but you said in the next century, the life of bridges, pavement, and other supporting concrete structures should at least double. Since writing that, how far are we to getting that?
I think we've reached it. I mean, honestly, is that I remember that. So Dr. Olick is a professor at Purdue now, and Bryant and I, we sat down. We were selected to kind of write this plenary paper about the future. This was a huge anniversary edition for the American Concrete Institute or something, and so they wanted to have the kind of the Godfather sit down with two people who they thought were rising stars and sit down with them and let them write about the future. And so when we wrote this paper, it was a fantastic opportunity for both Jan and I to work with Bryant. And, he also believed absolutely that we'd be there. So in 1999 through 2003 or so, I worked on a project called the 100-Year Highway. And so Interstate 99 in Pennsylvania was built. The 25 bridges were built, all by the same contractor with our techniques. And, I won't live to see it to hit 100 years, but we went back years ago, about after 10 years or so, and you could hardly tell it aged a day. And so, I guess we should probably go back and look at it now where we're 20-some years in. But as far as I know, and my colleagues at Penn State will tell me that it's a fantastic, very little maintenance required on these kinds of things. And we use the technology that we worked with Bryant on, that we already knew was happening in the 80s and 90s, but how long would it take us to get it to where it's used? But now, these techniques are used every day. They're not used on everything. I would say bridges, the high-value infrastructure items, Army Corps certainly uses this stuff on dams, locks, things like this. When we're involved with any of these kind of projects with the Army Corps, they don't want to rebuild a set of locks every 25 years. They want to build it for 100. And I think that's realistic today, that most of our heavy infrastructure can be expected to last that long.
Over the past couple of episodes, we've talked a little bit about ultra-high performance concrete, some of the advances that have been made with regard to that. I know down at UFall at the Bridge Project, they're working with that they've basically changed the the way they do the bridges now, because they were using tensioning to pull the panels together, which they brought up from San Antonio, these prefabricated concrete panels. Are you all doing any work with UHPC here? And
Well, I look at it like performance rate. I mean, everybody uses a different name for it, but yeah, you set higher standards. You can call it ultra high performance because that maybe gets you your grant or something. But I think that we're working on these kind of high performance elements of what do you need to do to make things last longer, be less permeable. So let's say if we're doing the casks for nuclear waste, okay, they have to be very resilient to any kind of impact. They have to last you have to build something there that's expected to last a millennia. And so yes, I mean these kinds of, so for me, whether you call it ultra or something else, I think it's really about defining it, and if you understand the chemistry and stuff, says, and you're willing to say, well, we can pay more for this, there are the opportunities to do this, what can you do on a giant scale versus what can you do on a small scale? Can it be precast in a factory where your quality control is much higher? And then, and versus field conditions where sometimes it's raining when you're working. So I think we look at all of these kinds of things. Recently, I just came back with some materials from the B1 or the B2. So we look on, and these things were essentially ceramic composite polymers from 30, 40 years ago, and they're way higher performance than anything we make an aircraft out of today. But this has been around for a long time. It's a question of how much you want to pay for it. And can a lot of people do it only a few people can do it? So I think a lot more contractors are getting better at making higher performance concrete. And I think that has been a key element to making the infrastructure last longer.
So you mentioned the B2. Can you talk about some of the work you're doing with I think you're also working with the Navy and with the Department of Transportation here to do some studies.
Yes, Dr. Solomon is an expert in steel, and so he's recently taken on some large contracts with the Navy to help them improve steel performance on ships. So particularly the kind of materials that are used in ships, the connections, the weldability, all the kinds of things you need for ship's hulls, and to make them resilient for the future. We're also talking about, when we're building the next Navy, we're going to have to make ones that are more cyber secure, ones that aren't susceptible to radar intrusions or EMF waves. And so now you're thinking about materials that can repel these things. So they're structural materials, but at the same time, so that takes us to something like the B1 or the B2, which actually has construction materials that a plane is made out of that make it nearly indetectable by a radar system. And so you build a material that can absorb or repel or become nearly invisible to these kinds of systems. I think that's been something we do here at the lab. We're doing a lot of stuff with bridges. Recently, the legislature here has increased the rating on bridges without considering they weren't designed to do that. So if you just say, okay, a truck can weigh 90 tons now instead of 80 tons, well, all the bridges in the state were designed for 80 tons. How does this impact? So one of our faculty here, Bruce Russell, did a lot of work on looking at how many bridges in the state and how much life will this eat up. So if every time you overload a bridge, it eats up a little more life. And so if you don't overload it, you may not use up much of its life at all. So we look at all of these kinds of things. We look very much at what industry and what our society needs. As engineers, we should be developing things that improve our lives and the world. We do some basic science, absolutely, across our college. But a great deal of our faculty are looking at how do we take science and apply it to things that will help and improve our world. And it's very much what the Army Corps does around the world. How do we make our bases safer? How do we build better port facilities? We're going to have, of course, rising tides over the next so many years. we have to have port facilities that can handle an aircraft carrier when the tide is now 2 feet or 4 feet higher. And that'll be a new challenge, I think, for all of our port facilities around the world. Same thing in airports and everything else we do. We all have to consider these things.
So in the next month, in the next almost 30 days, you're going to be honoring Dr. Christine Altendorf, who's she is the Chief of Construction and Engineering and Construction at Headquarters USACE. And can you talk about that and how that came down?
Yeah, so, Christine Altendorf was a graduate of OSU in actually biosystems engineering years ago, got her bachelor's, master's, and PhD here. She did her work in the area of water resource and water resource management and structures. So all of these kinds of things that give us the water, the locks, all the things the Army Corps maintains across our nation and the world. And so she was an extraordinary, not just student, but researcher, and understood what she had to be doing. And she built a career at the Army Corps. And I think it's been a fantastic opportunity for me to talk to her on the phone and to get to know her a little bit better. But she's exactly the kind of person who you want to be proud of. So she's going to be inducted into the College of Engineering, Architecture, and Technology's Hall of Fame. But she's also going to be awarded the Lohman Medal. And the Lohman Medal is the university's really highest technical honor. And it's only issued to 1 or 2 people a year, and some years nobody. Depends on what they do. And we're also going to be recognizing Rear Admiral Wynn from the Navy, also, who is leading maybe one of the largest cybersecurity systems in the world in making in the next generation of naval fleets. So it'll be great. We'll have Army-Navy game at the banquet.
That's outstanding. How many people do you have in your Hall of Fame? Do you any idea?
Oh, we probably have 100 or so in the Hall of Fame, and probably, I would say, maybe 20 Lohman Medal winners, and so forth. It's usually 2 people a year, so maybe there's about 200 in the Hall of Fame, 100 to 200, but very few Lohman Medals. They're very rare and really only go to the top technical people who have changed either their profession, their paradigm. They've looked at some other ways in which they have invented a new future for us. So, and they come from all different disciplines. But this is a good chance for us to see, an engineer from the Army Corps be awarded the Lohman Medal.
The question that I always like to end with is, what question have I not asked you that I should have asked you?
Well, I think we go back to Bryant Mather. We always think he was the godfather of concrete and stuff, but what most people don't know about him and Kate was that he was also an extraordinary collector and scientist in the areas of butterflies, published extensively in these areas. At the same time, he was the president of the American Concrete Institute. He published one of the most profound papers in the detailed identification of butterflies, of rare butterflies. And it was very, so you see a person who's kind of on all different sides and the amount of interest he had. And most people didn't realize that was the thing that Catherine and him had in common, is that they were both, she was a geologist by training. So they spent a lot of time in the field early in their career, and they were both so technical people that they would collect butterflies and examine them in every possible detail, and then write technical papers about the rarity of this species versus this species, the endangered nature of certain types of butterflies in Mississippi and the Delta, and these kinds of things. So, really a Renaissance person who didn't just talk about construction and concrete, but also enjoyed the kind of extraordinary things in nature. And I think that's a good lesson for all of us to be more than just our profession, but to expand our boundaries to whatever we want, And so I think that's always a cool thing for me to remember too when I'm spending time in my wood shop building something or going out and doing a little fishing or something like that. The fact that we have to know why we live, for what purpose, or not just what we do for a living. And so we try to instill that in our students here through our scholars program and through other things to be great at your profession, but also remember work isn't the only thing. Being a more rounded person, contributing to your community, contributing to other things in the world, which I think has been really a hallmark of the Army Corps as well. A lot of the talent that's in Army Corps is also involved in their communities, in Habitat for Humanity, in looking out for the future of nature, natural disasters, volunteering their time, and these are all great lessons that we learned from the Army Corps, but we try to install in our students here too.
Yeah, that's amazing. Could you imagine if he had been around during the age of Wikipedia? Just how much knowledge.
He'd have been writing something every day on Wikipedia, I think. So.
I mean, it really would. That sounds exactly like it would have been right up his, alley.
That's probably true.
Yeah. Well, Dr. Tikalsky, I really appreciate you taking the time to sit down with me. Thank you once again. I'm going to hopefully get out here and tour some more of your lab and get some imagery. Thank you.
Sure. I'm glad you could come to Oklahoma State and to see the Cooper Lab and what we have here. We're excited about what we do, and we have a large number of contracts that serve the DoD and many of its different branches to help them develop the kind of science and engineering that's needed in all of our areas of the armed forces.
Thank you. Thank you for joining us for this episode of Corpstruction. Corpstruction is a production of the Tulsa District Public Affairs Office. If you enjoyed this podcast, please consider liking and subscribing. To learn more about the Tulsa District, visit us online at our website, www.swt.usace.army.mil. Or you can check us out on one of our many social media platforms. You can typically find us at USACE Tulsa, all one word. Thanks for joining us. Have a great day.